All right, hello and welcome. This is just a continuation of the last lecture, and it's the last part of us building the foundation on how to use radar to understand and predict severe weather. This is still foundation building. It's not meant to be our expertise, and the purpose of this is just so when we actually start looking at radar for real, we know what we're looking at, where it came from, and what its limitations are. I made an extraordinary claim, which is that radar is better than being in person seeing the storm in terms of studying the fundamental mechanisms, like why the storm is happening, where it's going. Way better to actually use radar to do that than to just sit there and look at it, which is incredible to think about. So let's build that foundation up really fast. The most basic form of radar is called reflectivity, and what reflectivity does is it measures how much bounce the atmosphere has to our radar signal, how reflective the air is. And so in this radar picture here, sure, there is rain and even hail, but there's also clouds and dust and bugs. It's not just measuring precipitation. A lot of people think reflectivity automatically equals precipitation, and that's not true. Reflectivity equals reflectivity. So we can assume that it's precipitation, especially when it's particularly bright, but not always. Each one of these pixels in this image is called a bin, and the bin is the smallest area that we can measure. And bins are actually quite large. In this picture from Arkansas, which is a different kind of map, not reflectivity, I've circled two bins, and you'll see they're different sizes as we get farther from the radar, and as the radar, because it's round, we get different shapes, but they're a couple kilometers across. The radar's resolution isn't like crazy good. The radar's resolution is relatively small in this image, right? But it's not perfect. Like, we definitely are missing data. We could make it smaller. Now, just checking in again. These pixels have a name. What is the name for the smallest measurable piece of a radar? Now, we've gotten better. If you look at this radar damage from Kansas City in 2019, you can see that we have a lot smaller bin size. And obviously a lot of different ways of using the radar that you've never seen, right? The only radar you've likely interacted with is the top left. Now, again, we said that top left one shows how reflective the atmosphere is. So what's the name for that mode again? For now, you think of radar being reflectivity as that simple. Here's a picture from KSHB, like Gary Lee's X channel. And you can see like, oh yeah, that's a radar image. I get it. But eventually we're going to need to learn like that there's more kinds of radar and how to read more kinds of radar. But for now, let's just look at reflectivity. Let's keep on that track. You know how to read it. That's where it is. Like, you know in this picture that this is a strong thunderstorm. Like, if I asked you what's going on inside those purples and those reds, you say, man, that's a bad thunderstorm. And you're right. And actually, there are hints in here telling me that's a really bad thunderstorm. I see things that pretty much definitively tell me there's a tornado and certainly hail in this. And we'll learn how to identify those as we go along. In reality, when you look up a radar online or you watch it on TV or use your phone, it's going to be smooth. That means it's going to look pretty, right? We kind of take out a lot of the detail and try to make it look as good as possible. Right, this picture on the left is really pretty and it makes good sense, and I hate it. We're not going to use smooth radar in this class. We are going to use level 2 data, and I'll mean what that is in a minute, because if we smooth the data, all we're doing is we're getting rid of the things we measured, right? For me, I want the pixels. I know it looks like worse data, but because I'm not doing any math to the data, I know what is measured. And knowing what is measured matters a lot. So we want level 2 data. And I can ask the question this way. Which picture is more useful? The one on the left or the one on the right? At least to us in this class. And that's kind of weird, right? Because if I asked you which data is better, when you look in at it, the average person picks the one on the right. And that's because it looks nicer. You're familiar with it. But the picture on the left is actually far superior to the picture on the right. So just be careful. It's going to look like we're using older kind of technologically inferior products, but it's because we're using the real data that it looks that way. And so we expect this blockiness to become part of our life, this blockiness being the bins. The other thing that comes with it is that when we use the blocky, rare data, the kind of the stuff right out of it, well, that's going to give us a lot of stuff we need to ignore. I've circled in red here this big messy stuff that you've never seen before, right? Don't get me wrong, there's a tornado in this picture, but it's not inside that circled area. But that circled area still has important information in it. And I don't want to delete it. Like normally if you look up the radar somewhere else, it's going to be deleted. We call this kind of messy stuff ground clutter. And it can be trees, it can be planes, it can be birds, it can be dust, it can be nothing at all, it can be roads. It's complicated, right? In this one, there's a sunset. All kinds of messy stuff. Doesn't matter. The ground clutter is all the noise, all the stuff that we're going to learn to ignore that the radar's measuring that isn't precipitation. So again, what's the name for the circled area? The reason why we still include it is it's useful. On this particular day, what? May 22nd, 2011. Oh, that's an F5 day. Cool. There is a dry line. I've circled it. And you can actually see where the boundary is. If you are west of that line, no chance of thunderstorms that day. If you're east of that line, chance of thunderstorms. And so by keeping the radar intact, I still know where things are. There's still data in here. Even though it's messy and hard to read, there's really valuable information here. So we're going to keep that ground clutter. Now, this is the first time we ever saw a tornado, right? The first time we ever saw one with radar. So this is what radars used to look like. But even this first ever picture, we still can measure things on it. And so I have a question for you. Which part of this image is the ground clutter? The stuff that's not the cloud? Is it A, B, or C? Again, C is just open air. There's no return there, so that can't be ground clutter. A looks kind of choppy and pixely and unnatural, for lack of a better word, and it's near the center of the radar, so that's obviously the ground clutter. And B, that's our thunderstorm. The little hooky thing hanging off the back left, that's the tornado. We'll talk more about that later on. Here's another radar image from Kansas City, and if I'm asking you, like, which part of this is data that we're ignoring because it's not the cloud itself, which part would it be? And be careful, too, because, like, in B, we see the cloud moving towards us, right? That's our actually severe thunderstorm in this case. And in C, it's rain behind it. That A, again, is just that light blue kind of unnatural looking part that we're really interested in ignoring. Simultaneously, we also know that the radar itself lends a lot of distortion, right? That the radar itself causes the pins to get stretched, and there's a spot where you can't even measure it because the cone of silence extends all the way to the ground. And so there's going to be spots on the radar where the data is just wrong. So on this radar, which point A, B, or C is where the radar is located? And again, you're looking for that spot where the radar itself is kind of distorted with that circle in the middle. For today, I'm going to draw the radars in, but long term, I'm not going to show you where the radar is. I'm going to assume that you're able to look at this and say, oh yeah, that's the radar. Then you have to account for the fact that we know the radar has another limitation, that it can only see so high, and that as the Earth curves away, well, it's harder for it to see the cloud. And so there's this spot where we can't see under the cloud or over the cloud, right? And so knowing where the cloud is relative to the radar actually matters a lot too. So here's a picture looking at a Little Rock, Arkansas in 2014. And I've drawn the radar here in the center of the picture with that little white radar symbol. And I've put 4 letters along the thunderstorm. And my question is just, are all of these clouds, or these points, A, B, C, and D, these different measurements, are they all the same exact height off the ground? Right? Because the radar, it tilts upwards. As you get farther from the radar, obviously, the cloud bases that we're measuring go higher and higher up. So there might be stuff on the ground at D that we can't see, while at A, because it's close to the radar, we're looking closer to the ground in the cloud. So A, B, C, or D, which one of these areas am I most interested in measuring in terms of like the ability to see a tornado? Like if I was looking for a tornado, would it be easiest to see it at A, B, C, or D, right? Tornado being the part of the cloud that comes all the way to the ground. Again, we choose A, which is actually where the tornado is in this storm, which is super cool, because it's the closest to the radar. So the closer we are to the radar, the better the data is, within reason, until you get too close and then it gets distorted. Here's another radar scan. This is from a pretty famous day in 2008. And I've put A, B, and C here over 3 different areas that were all experiencing tornadoes at the time, right? Which spot would be the hardest to see a tornado? And why would that be? All right, almost done. If I ask a simple question like, where's the reflectivity the greatest? That's easy to find, right? Where's the reflectivity the greatest? Didn't even have to teach you how to do that, right? It's just obviously the brightest part of the cloud. Now, if I ask the question again a different way, where is this cloud the most dangerous? A, B, C, or D? From what you know so far, what would you pick? And you'd be right, right? C is where the storm is the strongest, pretty clearly. Now, there's an argument to be made for point D long term, but not right now. Right now, it's pretty clearly the hail core is at C, and that's the dangerous point. A is obviously clear, there's nothing going on there, and B is where the radar is. We're ignoring that area. By the way, there's all this mess around B. What was that called again? All right, really quickly, if you had a guess in this picture, where would the hail be? Do you see how easy this tool is to use? Just by looking for super bright reflectivities, we can actually identify where it's hailing pretty easily. Now, we don't know how big the hail is or where it's going yet, but we can find the hail. So here's a normal radar from Kansas City as you would see it on the news. And you can see that the colors have been exaggerated, right? If I compare the color scale here with the color scale here, you can see the news makes it look brighter, more fiery. It kind of hides where the hail cores would be. It's less obvious, is there hail or not? It's smooth, so we've lost edge. You see how this is, while a pretty thing to look at and pretty easy to understand. Oh, in the bright colors equal thunderstorm, and the night bright colors means no thunderstorm. I want you to start seeing like, oh yeah, well, this isn't that good. All right, well, looking at this map before we kind of kick out of here, this is Kansas City. You can actually tell where the radar is located. So there's lots of city names on this map. Which one's the radar? All right, a final concept. We use reflectivity over time to show where a thunderstorm's been and where it's going. You can see the track here of a very long track supercell that produced some very strong F5 tornadoes in 2011. Who cares? That's not the point of this right now. I want you to see that by tracking reflectivity, by tracking the spot the storm is, we know how the storm is moving, like how fast, in what direction, and if the storm is getting bigger or smaller. It's a very useful tool. Believe it or not, that's all you need to know. Next class when we come in, we're going to learn the different kinds of thunderstorms. We're going to learn how do you figure out where a storm is interesting. How do you use reflectivity to choose between, yeah, this is a pretty boring storm, or man, this storm might have hail, or holy crap, that's a big storm, right? Now, we're still not going to be to the spot where we can say, ooh, this storm's going to make a tornado or not, but we're well on the way. That's all you need to do for today. Thanks so much for your time, and I hope you have a great day. Buen camino en todo.